Bismillah. Hi, this is my video number 30, and I think they might be my last video for this subject for this semester. Right. So in this video, I'll talk on the divergence theorem, also known as the Gauss theorem. Yeah? Divergence theorem, also known as Gauss theorem. So what is the importance of this theorem is that we want to find a flux of a vector field over a closed surface. Yeah, we want to find a flux of a vector field over a closed surface that is the boundary of a region Q in 3 dimensions. If so, for example, if you have that surface, for example, so just consider this. All right, we want to find flux. The surface, let's call the surface S. The volume of that, we call it as volume of that, we call it, let's call it D. I mean the region, those things, and the surface that bound those region, we call it S. Okay, so we find a flux of a vector field, of a vector field over a closed surface, over a closed surface S. That is the boundary of a region D. Yeah, that is a boundary of a region D in 3 dimensions. 3 dimensions. Okay, so when we say find the flux over a surface, so which means what we are looking for, the how much, or how do you measure the amount of flux of vector field, I mean the vector fields that either going outward from the surface or inward into the surface. Yeah, so in this case what we need is the surface must be closed. Yeah, the surface must be closed. So to find the flux, we have seen earlier, that the formula is we integrate over S f dot n ds, yeah, over the surface. So when we have the surface like this, I think I've given you example of if you have a cube, for example. In the previous example, I think I've given this. So in this example, what we did is that we consider each of the surface. Yeah, we consider this as a surface 1, surface 2, surface 3, and surface 4 down here, surface 4, and then we have surface 1. Let's say down here 1. So S1, S2, S3, S4 here, S4, and we have this surface here, S5, and then we have the other surface that this is S6. So you need to consider each of every surface of that region. All right. Then we need to evaluate those one by one. So in other words, I can do this. This is S1 plus S2 plus and so on, plus S6 of f dot n ds. Okay, so that's what we have done before. But with the Gauss theorem says that, or divergence theorem says that, divergence theorem says that, okay, those flux can be found, yeah, flux for a vector field F over a closed surface, over a closed surface S, over a closed surface S that I need a word that bound a region D, yeah. So we have a surface S, for example here. This is our surface S1, 2, 3, 4, 5, 6, and then inside that we have a region covered by or bound by that surface. Okay, region D is given as those S f dot n ds. This is equal to triple integral over the region D divergence of f over D. So of course this calculation much easier, and again the limit of integration is very much important. Now the important things that you need to look at in this theorem, yeah. So we first, what we need is that the closed surface, yeah, S must be closed surface. Is one of them open, then you cannot use the divergence theorem. For example, if this we consider this cube, so let's say we don't have S3 opened, yeah, this part open, then in that case you cannot use the divergence theorem. So divergence theorem, in order to use divergence theorem, the region must be closed. Now let's consider a couple of examples. Let's consider a couple of examples. So let's say our f is given as 3x, 3y, and z. Let's consider that. And our surface S is given as z equal to 4 minus x squared minus y in the first octant. All right, so find flux. Find flux F over flux of F over S. Oh, it's not that focused. All right. So is that clear? So we have given F as 3x, 3y, z, and S as z equal to 4 minus x squared minus y in the first octant. Find the flux of F over S. Okay, so that's the question. So again, it is not necessary to sketch the surface, but it will help you a lot if you can do that, because by doing so we can recognize the limit of integration much easier. All right, so let's sketch those graph. So we have okay, so what is the surface look like? So this is in 3 dimensions, so we have x, y, and z. Okay, the easiest way to see if you have a graph like that, yeah, if you have the function like that, just consider the point on each of those axis. For on x-axis we have y and z is 0, so we have y and z is 0. So that gives you x squared equal to 4, so that x plus minus 2. So the minus part we remove because we just consider the first octant here, so just take x equal to 2. Right, 2 there. Alright, on the y-axis we have z and x is 0, so y is equal to 4. So y equal to 4. Y equal to 4. As well as on z-axis, we have x and y is 0, so z again equal to 4. That. And then we need to consider on each of the plane. Yeah, plane xy, plane yz, and plane xz. So for plane xy, our z is 0. Yeah, plane xy, our z is 0. If z is 0, so what we have is y equal to 4 minus x squared. So what do we have? Y equal to 4 minus x squared. So we have something like that, because we have minus, so it means the what we call this is going down. You open up on the lower parts, and then here we have on x we have 2 minus and plus 2 and 4 here. Alright, and then since we consider only the first octant, so means we have that. Now you transform this into a 3-dimension case. So this is x, this is y for x 2, and then we have 4 to 2 and a curve. So you have like that, yeah, more or less like that. Yeah, the same thing here. This is in 2 dimension of xy. This is 3 dimension. Now, and then we consider yz. Yz, x is 0. X is 0. So what we have, z equal to 4 minus y, or z equal to minus y plus 4. So which means it's just a straight line with a slope -1 and cross at 4. So we have 4 here, just a straight line. You can just make a straight line here. Oh, not really straight. Consider that as a straight line. Okay, so let me write this equation. This is y equal to 4 minus x squared. This equation here is z equal to 4 minus y. Alright, next we consider on xz plane. Xz plane, y is 0, so we have z equal to 4 minus x squared. Again, for this, let's, if you cannot see that, try to plot on xy xz. So z is, x is here, z is here, so we have 4 minus x squared. Again, we have that. Okay, so in this case there's a positive, so positive this side. Actually, this is x for z, so we need this part here, the positive part. This is positive part, this is negative part. Alright, so we need this graph. So transform that into 3 dimension. Here is 4, here is 2. Alright, this line here is z equal to 4 minus x squared. Okay, this line here, 4 minus x squared. So transform into here, so we have that. So this line here is z equal to 4 minus x squared. Okay, now, so this is our closed surface. This is our first, let's say down here on XY plane, that's considered surface number 1. On YZ plane, consider surface number 2. That's on XZ plane, consider surface number 3. So let me write those things. Down here, that's considered surface 1. Okay, this part here, that's considered as a surface number 2. This part here, that's considered as a surface number 1, 2, 3. Oh, sorry, surface number 3. And that part here, yeah, that covers everything. So this we say consider surface number 4. So if you find the flux, if you want to find the flux using the previous technique that we have used, where the formula is given as to find the flux is F dot N ds. So in this case, we need to consider each and every surface that we have. So which means we have 3 surfaces here. Yeah, 3 surfaces. So, sorry, 4 surfaces. So you need to consider those things. Instead, we can use the Gauss theorem or divergence theorem. So in this case, the divergence theorem. So you need to look those surfaces as a whole, not piece by piece, as a whole. And then you look at from Z positive. You can also from Y positive, from X positive, you can. But look at from Z positive. And then all those regions, all those surfaces will basically projected onto XY plane. That gives you a region on XY. So in this case, the region on XY is given by that. So let's call this region as R. Okay. So using the Gauss or the divergence theorem, that will give you, we have triple integral del dot f. Is it correct? Del dot f? Yeah, del dot f dv. So over those, your region D there. So this is, you can also write over the region R, and we have Z and F dv. Okay, so for R, I can put it one by one. For Z first, for Z, we have from Z equal to, look at the Z axis there, from 0, which is on XY plane, until that surface. Yeah, that surface. So this surface here is given by, so our S4 here is that surface. That. Okay, this is our S4. So we need to integrate Z from the Z0 until that surface. So we have Z from 0 until the surface is 4 minus x squared minus y. For y, now this is for R, this is your R. Okay, then consider y. Y is from y equal to 0, which is that line. Yeah, that line, until that curve. Alright, so we have y from 0 to 4 minus x squared. Alright, and then for x is from x0 to 2. X from 0 to 2. Again, let me stress this thing, that when we do a multiple integral, the most outest integral, which is that, must be from a number to a number, not a number to a function or function to a function. No, because you're not able to solve those things. You will not give you the required result. Okay, and then del dot f. So del, you know what del is. By definition, this is del x, del y, del z. Dot. Our f is 3x, 3y, and z. dv is dz, dy, dx. So we have dz, dy, dx. Okay, so what we have from there, that give you what? That give you ddx. So we have 3 plus the dy 3 plus d dz 7. Sorry, 1. So we have 7. So 7 is just a constant, so I can take out those 7, put it there. So we have x from 0 to 2, y from 0 to 4 minus x squared, and then we integrate with respect to z. So we got z is from 4 minus x squared minus y minus 0. So we have 4 minus x squared minus y dx. Okay, I hope that's clear enough for you to understand. And then you can proceed this. So we have 7x to 2, 0 to 2. For this we integrate with respect to y. So we have 4y minus x squared y minus y squared over 2, where y from 0 to 4 minus x squared dx. Okay, and from there I think you can just proceed this. Let me do. This is equal to, we have 7 integrate x 0 to 2, then we have 4 minus x squared. So for our y is 4 minus x squared, and then minus x squared. Our y is 4 minus x squared, and then minus y squared, 4 minus x squared over 2. That from, and then minus 0, you got 0, 0, 0, everything there. So that's all dx. Right. Now this gives us 7x from 0 to 2. You can simplify this. You got here, you got 16, all right, and then minus 4x squared. Here you have again minus 4x squared, so minus 8x squared, and then here we have plus x to the 4th. Am I correct? I think so. And that you have minus, yeah. So here we have minus half. You got 16 minus 8x squared plus x to the 4 dx. Okay, so I think from there you can just proceed this thing. This is, I've done everything. It's easy for you. Then you end up with the solution is 896 over 15. So please verify this. Yeah, please verify. Do it. Again, can you verify the, if I say verify the divergence theorem, the divergence theorem or Gauss theorem, same thing, yeah? Which means you need to do that f dot n ds, and then the right hand side is the triple integral over d del f dot d dv. So in this case, if I say verify, yeah, verify, so which means you need to do the right hand side here using the Gauss theorem, which is you have the solution here. And also, can you do by considering each of the surface with the same example, each of the surface using that formula, where you need to find S1, what is the integral over S1, integral over S2, S3, S4, S5, and S6. Add them together, the answer must be equal. So I leave it to you for that, to try and make sure you do that. And instead, I want to give more example. let me look at more example for you. Oh, okay. So let's say okay, so let the surface or the region D, okay, let D be the region bounded bounded by a circular cylinder, bounded by the circular cylinder x squared plus y squared equal to 4, and the planes z equal to 0 and z equal to 3, and let S denote the surface of D. Yeah, let S denote the surface of D. So if F is given as S cube, Y cube, and Z cube, yeah, find the flux over S using the divergence theorem. Yeah, using divergence theorem. Okay, so we have the divergence theorem here. You need to find the divergence of F. So what is it? Divergence of F, yeah, that give you del X. I write it one by one. I hope you can follow me. That, and our F is X cube, Y cube, and Z cube. And by definition, this is dot of that, and dot of that. So we have 3x squared plus 3y squared plus 3z squared. And then look at the surface. We might need to sketch the surface a bit. So the circular cylinder x squared, y squared, and then with that, so remember that we are in 3 dimension. Okay, so for 3 dimension, so let me plot it here. Let's say here we have z positive, so that this is your x, y, and z. Okay, and then x squared, y squared equal to 4. This is a circle on the xy plane, with radius 2. So on xy plane, so this is xy plane, so you have a circle. Yes, that your circle with this is 2 and 2 and minus 2. That side minus 2, this side minus 2. Alright, and then written, this is a circular cylinder, so which means you just raise this up, so you have until z equal to 3. So z equal to 3 somewhere here. Let's say that this is z equal to 3. So we have those. Yeah, that's a cylinder. So this is your surface. Okay. Now, having done those, we need to evaluate that integral. Okay, so we integrate over S f dot n ds. This is equal to, we have triple integral over d, yeah, del dot f dv. So that give you, we integrate over d. Remember that your d in this case is here. All right. So we have n del f is given here 3xy 3. So I can take out those 3. So we have 3 here. All right. And then what left is x squared plus y squared plus z squared. X squared plus y squared plus z squared. Okay, dv. So we have dz, dy, dx. Now, if you look at the our surface here, this is a cylindrical. This is a cylinder, so you can use a cylindrical coordinates. Yeah, you can use this cylindrical coordinate. This for the cylindrical coordinates. So what we have x. For the cylindrical coordinate, we have x equal to r cos theta. Alright, that's those things. Y equal to r sin theta. And we have z basically also z. So in this case, our dx dy, that give you r dr d theta. And our dz, we still have dz. Alright. So using this coordinate system, then you can transform that integral. Okay, you can transform that integral. Here you have x squared y squared, that give you r squared. Yeah, x squared y squared, that give you r squared. So we have 3. Now we have our r is from 0 to 2, and we have full circle. So which means theta from 0 to 2 pi, r from 0 to 2. So we have theta from 0 to 2 pi, okay, r from 0 to 2, and then we have x squared plus y squared. Using this, then you got, this is r squared, so that give you r squared. And z squared still doesn't change, so x squared, z squared. And we have dz dy dx, that give you r dr d theta, and we have dz. So we have basically r dz dr d theta. Okay, then from there it's easy for you to solve this equation or this. So here just integrate with respect to z. Or no, one more here we need z equal to 0 to, look at our surface, z from 0, which is that surface, until z equal to 3. So we have z equal to 0 to 3. Then we integrate with respect to z. So we have 3 theta 0 to 2 pi. Of course, if you look at here, there is free of theta, then you can evaluate theta first. You can just put it 2 pi down there. What left is r. But okay, we just do it one by one. R equal to 0 to 2. Then we integrate with respect to z. Here you have r cubed. Okay, here you have rz squared. So plus rz cubed over 3. Then we have z 0 to 3, we have dr d theta. Alright, from there we have this will give you 3. Let me just because here the integrand free of theta, then I can just evaluate those things. So we have 6 pi there, and then what rest is what left is at r0 to 2, and this thing for z. So you have r cube z here. Yeah, r cube z. Right. So we have 3 r cube plus, here is 327 divided by 3, so that you got 9. So you have 9 r, right? So that's dr. Okay, so I think you can just evaluate. Now it's easy for you to do this. That will give you 180 pi. Okay, so that's for the surface that involve a cylinder, or not really a flat surface. Now let me give you another example, but it's considered quite not that difficult. Let's consider another example. Let's say we have a Q. We have D, where D is a region bounded by a cylinder Z equal to 4 minus x squared, and the plane Y plus Z equal to 5, and xy and xz plane. Okay, and S is a surface of D, or surface that bounds D. Okay, and given F as we have x cubed plus sine Z, x squared y plus cos Z, and we have E x squared plus y squared. Okay, evaluate the flux as f dot n ds. Okay, so first thing, just look at those surface. Let's try to plot that. So we have x, and we have y. Okay, and then we have z equal to 4 minus x squared. Can you figure out those things? X equal to 4 minus x squared. So we have I think we have plotted this in our previous example, in the first example, if I'm not mistaken. So this gives you that. So we have that. Okay, and then we have this is a cylinder. I see. Let me write this cylinder. Z equal to that, so which means we have all the way that. Okay, that's your cylinder, and then y plus z equal to 5. So you have that surface y plus z equal to 5. So you have this cylinder and you cut that way. Okay, cut that way. So we have z equal to 5. Let's say 5 is here. Z is here 5. So, and then you just connect those 2 points. Okay, so this is actually the surface that cut that cylinder. So what you can see from there is that how can we plot this thing? How can we sketch this? So we have those, and then that the surface, we need to cut those. So what you can see is that so how to do this? That's part of our cylinder. So that gives us something like like that. Okay, and then okay, all right. I think that's okay. So this is your surface. So that's your surface. Those. So we have that. We have those. We have that. And we have those. And that. Okay. Not bad. Alright. Then we know that to evaluate this using this is a closed surface, so you can use the Gauss theorem, which give us integrate over d del dot f dv, and del dot f what we have from the given function here, from the given function. So what we have, so del dot f, that give you, let me write in a new paper, you don't have space there. Del dot f, this is del del x, del del y, del del z. Do not confuse with a cross. Yeah, cross give you different meaning. This is dot, divergence. Dots, our f is x cubed plus sine z, x squared y plus cos z, and e, the third component I put it here, e x squared plus y squared. Okay, do not worry about the function, because when you apply those the del to it, so you have this is equal to differentiate respect to x, that give you 3x squared, that give you 3x squared, that's all. That one we integrate respect to y, that give you x squared plus x squared. Differentiate respect to z, respect to z, that give you 0 plus 0. That's all. Oh, easy function. So you have for x squared. So integrate over d del f dv, that give you, we integrate x. Look at this again. This is our 2, this is negative 2, because we consider the entire region xy plane, that means that cuts from the below boundary there, and then xz plane that cut on the left side of those things, and y plus z equal to 5, which is those surface here. Alright, and then this is what is this? I think this is 5, y equal to 5. Alright, that's all. And then our region R is here. That's our region R. If you look at from z positive, all the surface projected onto that region R is just a rectangle. Okay, so we integrate those things from x from -2 to 2, then y from 0 to if we substitute those things into that, then you can find what y is. Yeah, so y from 0 to this part here, no, to substitute. So y from 0 to this part, this equation. So I can put this z from those surface, so I put it z first, z from 0 to that surface, 4 minus x squared, and then y from 0 to that, y from 0 to that, which is 5 minus z. Okay, our function is 4x squared. Of course you can take out 4, and then dy dz dx. So we have dy dz dx. Okay, so you can solve this easily. Then you can take out those 4, x from minus 2 to 2, z from 0 to 4 minus x squared, and then we integrate respect to y, so we have x squared y, y from 0 to 5 minus z dz dx. That gives you, for x minus 2 to 2, z equal to 0 to 4 minus x squared. That one you have x squared 5 minus z dz dx. Okay, then from inside those, so what you have, x5 x squared z minus 5x squared z, so x squared z squared over 2, and then z from 0 to 4 minus x squared. That gives you, integrate x from minus 2 to 2, and then for those inside, so we have 5x squared, our z is 4 minus x squared, minus x squared 4 minus x squared over 2 dx. So that's easy. You can I think up to here you can solve the rest. This give you 16 minus 8 x squared plus x cubed, x4. Alright, and for this you have 20x squared, minus 5x to the 4, and you have negative that. So that gives you 4 integrate x minus 2 to 2. You can rearrange this thing, so we have for x to the 4th, so we have minus 5 minus 1, so minus 6 x to the 4, and then for x squared you have 20x squared here plus 8x squared, so you have plus 28x squared, and then you have minus 16. That's all. dx. Now you can solve this. That gives you, the solution is 608 over 35. Okay, so I think that's enough for. I'll give you a couple of examples. That's okay, so that's all. Or maybe I just leave this with a question, exercise to you for the last exercise. Let's say I put it that way. Example: suppose a closed surface S form the boundary of the region forms a boundary of a region, D, and the origin 0 and the origin and the center of the coordinate system is the interior point of Q, is the interior point of D, okay. So if an inverse square field, if an inverse square field is given by F is equal to in terms of R, Q over R cube and R, okay, given as that, where Q is a constant, where Q is a constant, R is given as X, Y, Z, and those R is the magnitude of R, okay. Prove that the flux of F over S is 4 pi Q, is 4 pi Q, yeah, regardless of the shape of Q, regardless of the shape of D, yeah, regardless of the shape of D. So let me read that again, yeah. Suppose a closed surface S forms a boundary of a region D and the origin is the interior point of D if an inverse square field, which is given by that, so don't worry about those terms, inverse square field. The thing is that those formula F equal to Q over R cube and R, vector R, where Q is the constant and R is that vector and R is the modulus of vector R. Prove that the flux of F over S is 4 pi Q regardless of the shape of D. So what you need to consider here is that you might need S. So we have a surface, you have a D, so which means if you have X, Y, and Z, we have the interior point 0, 0 is there, and then this is our D. Yeah, so that's your D. So yeah, you can write anything as is. So let's say like that, and then that's your surface, yeah, covered by those D. So I leave this as an exercise to you. I think you can try this. All right. So basically, this is the end of our lecture. So there will be this is the last lecture. Then after this, no more lecture from me. a bit fast, because yeah, when we give a lecture without student, this is what happened. I think my lecture is quite slow, but still fast compared to when we give a lecture in face to face. That's a difference. Okay, but anyway, for just refer to your Putra Blast, and as well as the WhatsApp group for the latest of any announcements, yeah, for test, final, and everything. Okay, and again, if you have any problem, you can always message me, WhatsApp me, or you can also use chat in the Putra Blast. All right, so let me conclude what we have done today is that we have done the Gauss theorem or divergence theorem, which basically converting from evaluate the flux using the surface by using the triple integral given you, and I've given you a couple of examples. And for this example here, I wish I could give you as an exercise that you need to send it to me. Is that okay? So I will open the I will give this space for the in the Putra Blast for you to submit this as an exercise or as an assignment. All right, okay, so that's all. Thank you for me. Bye bye.